Hey there, it's Ken the Metal Professor. I have a sort of a sequel today to a video that I made yesterday about a problem that was asked about on Reddit involving partial fraction decomposition. And in that video, I sort of discussed the whole philosophy behind partial fraction decomposition and proceeded to do that for a rational function with linear terms in the denominator. There was another question in the same subreddit, actually by the same user, that was asking about partial fraction decomposition when there is a quadratic term, an irreducible quadratic term in the denominator, and I thought I would walk through that one too. This is going to be a little bit quicker. So this is recently on Math Reddit 16b. Yesterday's was 16. So you might want to watch that one first because I gave a little bit more detail on just overall strategy. This time I'm just going to dive right in and find the partial fraction decomposition of this rational function. 5x squared minus 9x plus 19 all over x minus 4 times x squared plus 5, and you'll notice here there's an irreducible quadratic, the x squared plus 5, in the denominator. Okay, now just the template for the partial fraction decomposition. Remember, what we're doing is we're looking at the big blob of a function and trying to drop in some mathematical dynamite to blow it up into smaller pieces, which if we started on the right and found a common denominator would produce the given function that's sitting there on the left. We also assume that what the mystery numerators look like are polynomials of degree no more than one less than what's in the denominator. So everything that's been canceled has been canceled. Everything that can simplify has been simplified. So if the denominator is a linear function, x minus 4, the mystery numerator is at worst a constant. And if the denominator is an irreducible quadratic, then the mystery numerator is at worst a linear function. And so there's only two pieces in this partial fraction decomposition, but we get three coefficients, capital A, capital B, capital C. We have to discover what those are in order for the thing on the right to combine through a common denominator to produce the originally given function, which sits there on the left. Now, this question was asked in a pre-calculus context just doing the decomposition, but for those of you that are finding this because you're in Calc 2 and you're like, oh my God, what is this partial fraction stuff? Because I have to integrate functions using it. Just like in yesterday's video, the story is that the calculus part is actually a snap. It's the algebra that's irritating. And in fact, just to show you, if you were asked to do this integral on the left, and you could in fact do the partial fraction decomposition to the thing on the right. And I just see that I lost that plus c. That should be down here in this thing, and I'm not going to pause the video and go edit this and fix it. So imagine there's a plus c. So bx plus c is that numerator. If we could do that, there it is. There's that extra plus c. Somehow it got moved from one row to the other. Okay, but a over x minus 4 is a term by itself that would be integrated. If this numerator is bx plus c, then the numerator of bx over the denominator of x squared plus 5 could be separated from c over x squared plus 5. So again, pretend there is a plus c in that numerator and pretend that that plus c in this middle term in the next line is gone. Okay, if the partial fraction decomposition can be determined and we can come up with these constants a, b, and c, then the net result of the antiderivative would be this humongous mess. Now, if you're in calc, you know how those individual terms work, but the point to this is that's the calculus, that's it. If we can decompose the function into the smaller pieces, then we can do the integrals. And in fact, if we've set this up, we don't have to do any more calculus. All we have to do is find a, b, and c and then go plop them into this template for the result. And so one of my suggestions is when you're doing partial fractions in calculus is go ahead and finish the calculus stuff up front, even if you don't have the values for your constants, because then that's a load off your mind. You don't want to get snarled up into the partial fractions, get all frazzled, and then have to go back and finish the calculus. All you got to do is find a, b, and c and drop them in here, and you've got the answer. in the calculus version of this question. But just the what is the partial fraction decomposition of this function, here we go. So just like yesterday's example, we're going to multiply both sides of our template by this denominator on the left. That will allow the denominator to fully cancel itself on the left, and then when that denominator in red multiplies through the separated terms on the right, bits and pieces are going to cancel. So the x minus 4s will cancel the first term with a, leaving a times x squared plus 5, and then the x squared plus 5 will cancel in the second term, leaving the x minus 4 behind. So no more fractions, and that's always good news. Okay, now how do we use this cleaned up template to determine capital A, capital B, capital C? Well, one method is, remember that this has to hold for every value of x. So we can pick clever values of x, drop in there, and see how it shakes out. So what might some of those be? Well, if we focus on this term on the right where we're multiplying by x minus 4, you might see that if we plugged in an x minus 4, that whole clump goes away. We might also notice that this term in the middle is b times x, and if we plugged in x equals 0, that term with the b would go away. Now, unlike yesterday's example, where there were 3 terms and 3 clever values of x that were obvious from those terms, we're kind of out of really super clever values of x to try. So we just have to remember we can use any x that we want. We could plug in x equals 17,498. That would not be clever. Okay, so we're going to use x equals 0. We're going to use x equals 4. And the third one, you just got to pick one. So other than 0 and 4, what's the easiest value of x that you know about? How about 1? Okay, so we'll try that. So if x is 4, here we go. Here's where the mathematical carnage begins. Here's our template. When we plug in x equals 4, that whole right-hand side is going to drop out, or the whole right-hand term is going to drop out, and we'll get some numerical values over there on the left, like so. See, the b's and c's are all gone. The only unknown left is a. The numbers shake out so that a comes out as a nice clean 3. All right, so now we know that a is 3. So then, knowing that a is 3, we can hop to our next clever value of x, plug that information in. So x is going to be substituted with 0. The capital A is now known to be 3, so we might as well put that in there and use it. Zeros everywhere there was an x. This shakes down nicely and allows us to solve for c being -1. Okay, and now we know that a is 3, c is -1, and we're also going to test out the value x equals 1. So let's plug in 3 for a and -1 for c, so that b is the only mystery number left. Let's plug in x equals 1 for all the instances of x. Let's shake these numbers out, and the final result is b is 2. Okay, so there we go. A is 3, b is 2, c is 1. So if you were doing the partial fraction decomposition, that's it. You just go plunk those numbers back into the original template. If you're doing the calculus version of one of these, where you were integrating this nasty thing on the left, we now know the decomposed form of that function, and we already did the integration on one of the front slides, and so now we know to take the a, b, and c and plonk them down into that result and move on with our day. Now, if you like the other method of solving for these coefficients, here's a reminder of what it is. This again was the partial fraction template after we'd multiplied both sides by the big denominator from the left-hand side. Instead of selecting clever values of x to plug in, we're just going to say, hey, there is a quadratic polynomial on the left and it has known coefficients. If we multiply everything on the right-hand side out and collect our terms, collect our powers of x, there will be a quadratic polynomial over here whose coefficients will be in terms of a and b and c. And each of the coefficients on the right has to be equal to the corresponding coefficients on the left. So, and we can match those up and solve. So here's what was on the right. We're going to multiply it out. We're going to gather together. Let's find our x squareds. Well, there's ax squared plus bx squared, and so there is the x squared term. The constants are the 5a and the minus 4c, so there they are on that right-hand side. And then the linear terms, you've got the, let's see, where are they? We've got the minus 4b and the plus c. Now they're gathered together. And now match up the colors, right? The coefficient of x squared from the left, which is 5, is generated by a plus b. The coefficient of x, the negative 9, is generated by negative 4b plus c, and then similarly the constant of 19 is generated by 5a minus 4c. That is 3 equations and 3 unknowns. If you like solving those, this is then your favorite way to do this. If you like solving those, I will leave you to do it. I'm not actually going to solve that system, but it wouldn't be too hard. But if you want to, you can confirm that the 3, 2, and negative 1 for A, B, and C are the right values. You can just plug those right back in here just to test them, right? Again, we haven't solved this system for A, B, and C to come up with these. I just know what these are because of the first method. And I'm just confirming that, yep, those are the solutions to this system as well. You know, A is 3, B is 2. So yeah, A plus B is 5. And then you can confirm the B's and the C's and the A's and the A and the C combinations with the other equations, right? So you get to pick which is your favorite technique, or better yet, make sure you understand which of these techniques for solving the constants is preferred by your instructor who's going to be grading your work, and perhaps to try to stick with that method. Okay, but that's it. That's the second run through partial fraction decomposition. I hope this helps.